do not on me, but there's probably one at the library. That would be, yeah. So that would probably be the next place. Is like, just because I don't know of one that's just like setting out somewhere. Like in this building, at least. Like I know some people have them in their offices, but I don't know anybody anywhere they're just set out for general use. Chapter 2. So this really brings us into, okay, we've talked about matter, we've talked about pure substances and mixtures, and so now we're going to specifically look at the nitty-gritty components that make up matter. So these are the smallest components that you find in pure substances are called atoms. So atoms, when doing research, studying, trying to figure out what atoms were made of, they found that there was actually subatomic particles. So sub is kind of like under. Another what?
The paper for chapter 2.
Like a PowerPoint, you have to print those out at the library. Yep. So if you decide that you want it, and now, so like through last week, it was free. You could have printed all your PowerPoints at the library for free, but now you can print 10 pages a day, and anything more, they're going to charge you. So like if you like go by the library, print 10 pages, go by the library, print 10 pages, you can still do all of this over the semester, but now you're going to have to kind of stagger it to get, if you want to use these. These are the same PowerPoints that are posted in Moodle, and these are the ones that I'm going to use all semester. There's a lot of blanks in there that I'm going to add just like I did in Chapter 1. So if you found that was helpful in Chapter 1, having that PowerPoint, I really encourage you to just make plans to go over and make those copies because you've actually already paid for it. You have an activity fee in your tuition, and that actually pays for printing at the library. So you're not like taking money away. You've actually already paid for the right to do those copying. So that's why I'm like, sure, if you're going to write on them, then it's really beneficial.
So it's still free, but it's not free?
It's now, because through the 25th, it was free printing.
So how much is
Now you can do 10 pages a day without charge. Anything past, and they charge you per page.
Oh, okay.
Okay? All right. So in this, in experimentation, they figured out that atoms are the smallest units of matter. So that is one of the criteria. So an atom, it is the smallest unit of matter. When looking at the periodic table, if you look at carbon as an element, all the atoms of carbon have similar characteristics. And if we split those atoms further, then they lose those identifying characteristics. But it is these three components together that create the characteristics of an atom and the characteristics that that element has. So there's protons, neutrons, and electrons. So in reading through this little chart, protons, neutrons, and electrons have some variation, whether it's by charge, by size, or even by location in the atom. So over here, if you just draw a circle, we're going to say, okay, if this is the atom. So the atoms are roughly spherical. These three subatomic particles are found in certain locations within the atom. There is a very, very small, dense center that they named the nucleus. And in the nucleus are two of the three subatomic particles. This is where protons are and neutrons. So protons and neutrons are like all smashed together in this very, very small, dense space. Electrons are found outside of the nucleus. So location is one way that they differ. Another way they differ is charge. So they found that in the nucleus, protons and neutrons, they knew that there were protons compared to neutrons because protons have a positive charge. So you will often see the little p written with a plus as an abbreviation because of that positive charge, while neutrons are neutral. So you'll sometimes see the little n, and it has like a little 0, which is sort of like no charge compared to a positive or a negative. So you'll have like a little n with a little not sign is what they call that. So that has a neutral charge. So that's how they figured out that protons and neutrons were not identical, because they differ in charge. Same location, they're both in the nucleus, but they differ by charge. Electrons, however, have a negative charge. So atoms as a whole are neutral, which means the number of protons has to equal what? If the atom is neutral as a whole, the number of positive protons must be equal to the number of negative electrons. So pluses in a neutral atom, pluses and minuses are the same. So protons and neutrons are going to be, protons and electrons are going to be equal in a neutral atom. And neutrons don't add to a charge. So that was another difference. So you can see the E, oftentimes it's written with a negative. The third thing is its relative size. Now, if we were looking at the size of an atom, if we were like, how much does one atom weigh? We would be talking about the mass of one atom is somewhere on the scale of 1 times 10 to the minus 25th grams. So remember which way the decimal would go with that? Decimal place would end up going 25 places to the left. It's a number way smaller than 0. So they're like, that's way too small to be able to measure in just a collection of atoms. Even if we have 1 million of them, that's still not going to put us anywhere near a whole number. So they said, let's talk about relative mass. Relative mass is how these 3 particles compare to each other. So they said, okay, relatively, protons and neutrons have about the same mass, and they are really responsible for the mass that you find in the atom. Compared to them, electrons have a mass that's about 2,000 times smaller. So no element or no atom on the periodic table, no element have masses of 2,000. The highest masses are only in like the 250s. So because of that, the relative mass of an electron compared to protons and neutrons, we can say the relative mass is 0. Now, remember, it's not 0 because anything that has mass and takes up space is matter. So electrons are matter because they do have mass, but it's so small, their relative mass would not affect the overall mass of the atom, even talking about really big atoms, much less talking about teeny tiny ones like hydrogen. Okay, so protons have a relative mass of 1, neutrons have a relative mass of 1, and in comparison, electrons, you could say, have a mass of 0. Does that make sense? Like this relative idea? Because we can't talk about grams because there's way too many exponents. But if we just compare those 3 subatomic particles, we could say protons and neutrons, they're about equal. And they really give the atom mass, so we'll make them a mass of 1. Electrons are so much smaller, they don't affect the mass of the atom, so we could just ignore them in terms of mass and how that effect comes in. In fact, I think of electrons as like being tiny little electrical particles. They do have mass, but it's so small. Electrons are in constant motion, moving around that nucleus. They stay in their little area outside of the nucleus, and they're in this constant motion, so they don't just sit still. Whereas protons and neutrons are all kind of clustered together in this very dense core. It's dense because that's where all the mass is. The nucleus holds all the mass for the atom, protons and neutrons. Okay? So when thinking about the structure and the number of them, they were trying to come up with like counting units. And so this relative mass, they came up with like a generic counting unit called an AMU. The term AMU stands for an atomic mass unit. So that's what AMU stands for, atomic mass unit. And this is really this relative mass I was talking about. So we know that protons is going to have 1 AMU. Neutrons will have 1 AMU. But electrons, they really have none. compared to protons and neutrons, that they're going to have 0 AMU. So really, all of the mass comes from protons and neutrons. All of the mass of the atom is focused in the nucleus of the atom. So they also came up with carbon as kind of being like the standard for what they're going to count with. So looking at carbon, on the periodic table, do you notice that you've got the C and the number 6 above? That number 6 above, and underneath, yours says 12.01 on your periodic table. Those two numbers we can use to actually identify how many protons, neutrons, and electrons carbon actually has. The top number is called the atomic number. The atomic number actually identifies what element an atom belongs to. All atoms of carbon have an atomic number of 6. They always will. If they have an atomic number of 7, then they're nitrogen. They're not carbon. They've got to have an atomic number of 6. So you can think of the atomic number identifies the element. You can look at the atomic number. So if you see atomic number of 12, what is it? Magnesium. Okay, so you see the 12 above. You just look on your periodic table, look at the number that's above. That identifies that either atom or that element as being magnesium because it has an atomic number of 12. But the atomic number tells you the number of protons. So carbon has 6 protons. The atomic number is 6. It has 6 protons. But what did I tell you about a neutral atom? The number of protons is equal to the number of electrons, right? Remember, the plus and minus are equal. In a neutral atom, the number of positive protons and number of negative electrons is the same. So the atomic number defines the number of protons. It also defines what element type it is. But you can also remember that because the number of positives is equal to the number of negatives, if the atomic number tells you 6 protons, it also tells you 6 electrons. So that's just that number. So you do not have to memorize like how many protons, neutrons, and electrons in any element. You do have to know the names and symbols for those 30. So if I give you the name like iron and ask you what the atomic number is, you need to know that iron is Fe. You need to be able to find it on the periodic table. You need to know that 26 tells you the number of protons and electrons. Okay? So that just leaves neutrons. So this number underneath, we'll talk a little more about why it's got a decimal. But for right now, that number underneath, that is the atomic mass. So what are the two particles that give the atom mass? Protons and neutrons, right? Because we said electrons are basically 0, so you can ignore them. So if the atomic mass is the number of protons and neutrons, how do I find the number of neutrons? Just subtract. Subtract the two numbers. Take the bigger number, just round it to a whole number. So 12.01 becomes 12. And subtract the atomic number. Subtract the two numbers on the periodic table. You'll always be subtracting the larger from the smaller. The larger is always the mass. The smaller is always the atomic number. And this tells me that I have 6 neutrons. So you don't have to memorize it. You just have to have a periodic table in front of you. Okay? Protons and electrons are the atomic number. Neutrons take the atomic mass, rounded to a whole number, minus the atomic number, and that's going to tell you the number of neutrons because protons and neutrons are what give the atom its mass. So knowing this, looking at lithium. So lithium with number 3, how many protons does it have? 3, right? How many electrons? 3. Right? Because remember, those are the same. That's just based on that number. And if you look at this, see the 3 little tiny blue dots, those are the electrons. See the 3 red balls that look like they're in the center part, those are those protons. There's 3 of them. Now neutrons. How do you figure out how many neutrons? You're going to take the number and do what?
Subtract
Mm-hmm.
from 3.
So it would be what? Find it on the periodic table. 7 minus 3. See it? In the first column, 7 minus 3 tells you 4 neutrons. And those are the little gray balls. So remember that protons and neutrons are all kind of smashed into that nucleus. The electrons are the ones that are the outside. And they drew them, I like that they drew them like much smaller. Okay, showing that they're much smaller than protons and neutrons. That's all you have to do. Just subtract them. Okay, we already did carbon, so let's do these. So you tell me, number 1, Ag, what is that? It's one of yours, not gold, silver. So it is silver. Ag is silver, so if you have a hard time telling gold from silver, then maybe you need to put that on your note card. Remember, I've got the note cards up here. Grab one on your way out. So now, second thing you have to do is you have to find silver on the periodic table. How many protons does it have? 47. Does everybody see it? 47 protons. What else is 47? Electrons. So I know that there's 47 electrons. Protons and electrons, positive and negative, are equal in a neutral atom. So the atomic number tells you 2 of them. Now how do I figure out how many neutrons? What am I going to round to? 108. Everybody see 107, that silver is 107.9. Round it to 108 and then subtract 47. So that's 61. 61 neutrons. What's Na? Sodium. So that's another one of your 30. Remember, you need to know elements 1 through 20, and then I gave you a list of 10 more in chapter 1. You need to know the names and the symbols. So if I give you the name, you got to be able to find the right symbol on the periodic table. If I give you the symbol, you got to be able to find the right name, vice versa. Okay? So sodium, how many protons does it have? 11. Everybody find it? First column, Na, third one down. Then, what else is 11? Number of electrons. How many neutrons does it have? 12. And you know this by taking 22.99, round it to 23, and subtract 12, or 11 to get 12. Okay, just subtraction. That's all you have to do to get neutrons. Subtract those 2 numbers. Now, if I give you a symbol like TH, that is not one of the 30 that you had to learn. So if I gave you that, I would tell you the name. Okay? I would give you the name and the symbol for something that's not one of the 30 that you already have to know. So I will tell you that TH, I really like this because it is thorium. Thorium. You can just see in your head, thorium. So find it. It's really low on the periodic table. How many protons does it have? 90. Find 90. Very last row at the very bottom, 90 protons. That's a lot more than 11 sodium protons. That's a big atom. How many electrons? 90 as well. So 90 protons, 90 electrons. How do I figure out neutrons? Subtract what? 232 minus 90. So that means it has 142 neutrons. That's a lot. Okay? That's a whole lot when you look at these smaller ones like hydrogen and carbon that only have 6 of each. All right? Same thing with the next one. The next one I like as well because this is Superman's issue. This is krypton. Krypton's on the far right column. How many protons? 36. How many electrons then? 36, right? They are equal. Don't get that mixed up. Remember, plus and minus are equal. Can't tell you how many students get these switched. Okay, these are like super easy questions, and they always like, there's always a couple that like switch the number of protons and neutrons, and I'm like, ugh. Okay, remember the whole number, the atomic number is numbers of protons, which are positive, and also equal to the number of electrons, which are negative. They're gonna be equal, and it's that whole number. Neutrons, I've got to subtract the 2. So what do I have to do to Krypton's number? Round it to 84, and then subtract 36. So it is 48. 48 neutrons. Hg, what's that? Mercury. Very good. That's another one of your 30. Zn, what is that? Zinc. So that is another one of your 30. So if you've got, you may have to go back to chapter 1 to that periodic table page where I listed all of the names and symbols. That go back over those ones, make that list out. You can figure out numbers of protons, neutrons, and electrons. We'll review that one next time. Now, if I give you the name of one that you know, you should be able to find the symbol on the periodic table, and you know how now to find protons, neutrons, electrons based on just the periodic table numbers. But sometimes they write them different, which is, of course, they use sometimes this notation that they call symbolic notation. Symbolic notation uses the symbol. It puts the atomic number as like a superscript in front, and the atomic mass is a superscript. The atomic number is the subscript. So how is that compared to the periodic table? It's backwards. I didn't do this, okay? This was not my choice. I would have been like, no, keep it the same. But no, somebody said, oh yeah, let's do it like this. So you just have to remember, the bigger number is the atomic mass. The smaller number is the atomic number. Put a note on this page. Note that those numbers are switched from the periodic table because it sometimes throws people. But looking at this, notice that they call it the mass number instead of the atomic mass. This is really looking at one atom of carbon, and we're defining its mass and its atomic number. So one atom of carbon will have a certain number of protons, neutrons, and electrons, and that's why you don't see that decimal place. Question? Atomic mass. So the mass number, remember that this is protons and neutrons, right? The bigger number, whether you're looking on the periodic table or if it's listed this way, the bigger number is always protons and neutrons. The smaller number is always protons. And by default, it's also telling you electrons because P and E are equal, okay? So in this, think of the symbolic notation as being like, I'm looking at one atom of carbon in this respect. So this one atom of carbon has how many protons? 6. How many electrons? And then how many neutrons? 6, okay? So I know they're all equal. That's not always the case. Small atoms, that does tend to be more common. Here's one other way that you might see it written. Sometimes they'll call it this. So here's a third way that they might write an element. Carbon 12. So from carbon, you know how many protons? Because carbon is always atomic number 6, right? So if you see the name of the element, that atomic number on the top does not change. All carbon atoms have 6 protons and 6 electrons if they're neutral. All carbon atoms do. But notice this one has the 12 after it. So this is telling you what its mass number is. So this is telling you the mass. And from here, I know that this is going to have an atomic number of 6. So if you saw copper 64. Copper 64, can you tell me how many protons? So find it on the periodic table. What's the symbol for copper? It's another one of yours in the list. Cu. Find Cu. Finding Cu, I know that copper, because I know that it's Cu, so I know that there's 29 protons. By default, 29 electrons as well, because that's the atomic number. So now, how do I figure out how many neutrons? Just subtract the two. So 64 minus 29, would be 35. 35 neutrons. I do that just by subtracting. So if you're given the name and the mass, you should be able to figure out protons, neutrons, and electrons. If you have this symbolic notation, protons, neutrons, and electrons, if you look at the periodic table, you can figure out protons, neutrons, and electrons. And those are pretty much like the three ways that you might see an element written. So we need to talk a little bit about why the periodic table has those decimals. Okay, so notice like the other two, when I said like carbon 12 or talking about copper 64, that's just a number. That's a mass number that's a whole number. But the periodic table has mass numbers with a decimal place. So even carbon is 12.01. That is because there exist carbon atoms that have 6 protons and 6 electrons, but they have different numbers of neutrons. So if they have different numbers of neutrons, that means that they can have a different mass. They're still carbon because they have 6 protons. Remember, the atomic number defines the element. So all carbon atoms have to have 6 protons, but they don't all have to have 6 neutrons. So if they have more neutrons than the normal, then that's going to create different mass numbers. So I can have carbon 12, remember that that's 6 protons, 6 protons, 6 electrons, 6 neutrons. But what if I have carbon 13? How many protons? 6. 6 protons, 6 electrons, because remember those are equal. But that means how many neutrons there? 7. By subtraction. And then what about carbon 14? How many protons? 6, because that is what defines carbon. The number above the symbol on the periodic table, that's not going to change. So 6 protons, 6 electrons, but this one has 8 by subtraction. 14 minus 6 tells me that I have 8 neutrons. These 3 forms of carbon, they're all carbon, but they are called isotopes. So isotopes are atoms of the same element that have different numbers of neutrons, so they have different masses.
I have a question. So when you give us something like this, are you gonna do this on the exam?
Yeah, maybe. Anything that I tell you in class is fair game on an exam.
Okay, so when you do, so we'll just find it on the periodic table and just subtract the protons and get the
From that number, right? Because I know that carbon has an atomic number of 6. So I know carbon has 6 protons and 6 electrons. That's not going to change. The only thing that changes in this is the number of neutrons.
2 questions for you. Does the variations in neutrons, does that affect the stability of the actual atom?
Yes, you're jumping ahead. Wait till the next slide. Okay, second question?
Second question, are we allowed to take
You-
into
It's on the wall. You will always have a periodic table. You do not have to memorize where things are on the periodic table. What I'm trying to do is I'm trying to teach you like how to use it, right? Because you can figure out protons, neutrons, and electrons just by using the periodic table. So you just have to know how to use the periodic table. You don't have to memorize, what the numbers are, because you will always have this. I can't remember all of the atomic masses, okay? Like that's not something I had to memorize even with a master's degree in chemistry. I just had to know how to use it, okay? To be able to look, and because it's really like a big reference chart. But I like it's set up so nice and neat and even, like everything sits there all in a row. Now, what if I was going to write carbon 13 in symbolic notation? What would I put for the letter? What's its symbol? C. What am I going to put as above in front? 13. And what would I put below? 6. So do you see that that's the same thing? Just a different way of writing it. They call that the symbolic notation. What if I was going to do carbon 14? 14 at the top, still 6 at the bottom, because carbon always has an atomic number of 6. So if you saw a pair of atoms that were written this way, you would know they're isotopes. 1, because they have the same symbol. 2, they have the same atomic number. So the mass can be different, but if the atomic number and the symbol are the same, then you know that they're isotopes. So this is actually how we ended up with all these decimal places. Carbon exists as C12. 99% of the time, carbon exists with 6 protons, 6 neutrons, 6 electrons. 99% of the carbon atoms in the world are C12. But there's a very small percentage, like 1%, that exists as C13. Which means there's just a few with an extra neutron. There's an even smaller number, much less than 1%, that actually exists as C14 with 2 extra neutrons. But those 2 make the mass not quite exactly 12, which is why when they take what they call the relative mass, it's based on the different isotopes and their abundance. So we're not going to do the math calculating any of those, but that is the reason why if you see any elements with a decimal place as their atomic mass, then you know that there's isotopes. You know that there's isotopes that exist in varying amounts, but the closest atomic mass is going to represent the most common isotope. So like, for example, if you look at bromine. If you look at bromine on the periodic table, number above is 35, number below 79.9. Okay, so how many protons? 35. 35 protons, 35 electrons. But now, the most common isotope would be the closest rounded number. So that would be 80. So this, I could call this bromine 80. How many neutrons would that be? 45. So if I took 80 minus 35, 45 neutrons, that would be the most common. That doesn't mean that there's not other isotopes. So if you see any kind of decimals, then odds are there are. So there might be some that are a little smaller. There might be some a little bigger. But this one's definitely going to be the most common. Just like carbon 12.01 rounds to carbon 12. 99% of the carbon in the environment is carbon 12. Just know that. Okay, that this represents really the most common isotope. But it doesn't have decimals because there are commonly other isotopes. So here's the part. This radiation chemistry is actually a relatively new branch of chemistry. Like when you think about people were studying and figured out about atoms way back in the 1700s. So radiation chemistry really wasn't described concretely until the early 1900s. So it's only like 100 years old. So we've really only understood this whole idea of isotopes for about 100 years. So Henri Becquerel, French guy, so he was studying rocks, okay? So he was actually extracting, they were still in the midst of putting elements together, looking to see if there's some elements. Yeah, they knew about carbon, hydrogen, nitrogen, and oxygen by then, but he was looking at other metals, ones that weren't found as common. And so they were extracting the earth and they were extracting metals out of the earth and trying to see if they could identify new elements. So he had this rock. He had it in the lab, and also in the lab, he had some photography film. So this is back when you didn't have the digital films. You actually had a piece of film that you would expose to light. That was how you would do pictures. I don't know if you've seen some of those old black and white and the funny little camera where they used to it was a big thing on a tripod and it had a little cape you had to put over your head to keep it dark, very light sensitive. So he had plates, and so that film was big. Okay, it was big as the photograph typically. So it was a big piece of film. He had this film in the lab and he put it next to this rock that he had this compound, uranium. He used the film and he went to develop it and it was totally white. How does that happen? Why would film turn totally white? That means it was exposed to what? Light. The more light you expose, the lighter the film when you develop it becomes. So he's like, must be a bad batch of film. So he orders another batch of film, gets it in, has it in the lab for a while, uses that film, develop it, also white. So then he puts it somewhere else and he doesn't have this issue. So he actually starts putting film in the lab in different places. And he discovered by experimentation, the closer he put it to this rock of uranium, the more exposed the film was. So he said, this rock must be emitting energy. It's not glowing. I can't see light coming out of it, which is usually how you expose film. But there has to be energy that is being emitted from it. That energy he called nuclear radiation. So I always think of radiation like from the sun, the warmth, the heat from the sun. He's saying this is energy coming out of this sample, this element, and it is because it is unstable. Isotopes that are not stable become stable by breaking down. When they break down, they release this energy. And this energy they call radioactive decay. So decay, I always think of things decaying means they're like breaking apart. So you can think like this element is not stable. If it can break down, it becomes more stable. When it breaks down, it releases energy. So what atoms are like this? Well, the ones that are the most unstable are the big ones. Right? So remember when we were doing this right here? So looking at sodium, see how sodium is like 11 protons, 12 neutrons? They're about the same. But then look at silver. What do you notice about silver? It's 47 protons and how many neutrons? 61. So it has about a third more neutrons than it does protons. Now look at thorium. What do you notice about the number of neutrons that thorium has? It's closer to 50% more, okay? 50% more neutrons than protons. So remember, protons and neutrons are in the nucleus of the atom. So if you think about an atom of thorium, in that little spot, all those neutrons and all those protons are like crammed in there. The bigger the atom is, the more neutrons, the more they're kind of like fighting for position to stay there, the less stable the atom is. So that's what they find. Large atoms that have atomic numbers greater than 83 tend to be less stable because they have too many neutrons. And if they're not stable, they're going to undergo this breakdown to become more stable. If they release energy, atoms that release energy, they call them radioactive, or they say that they're radioisotopes because it's a certain atom of an element with a lot more neutrons than normal, and that makes it less stable. So knowing what you know about that, if you were comparing carbon-14 and carbon-12, which one has more neutrons? 14. Carbon-14 is less stable. Carbon-14 is radioactive. Carbon-12 is not. When you have equal numbers of protons and neutrons, that's a pretty stable nucleus of an atom. When you start to get more and more neutrons, that tends to be less stable. So this is going to be the unstable one because it has more neutrons. In fact, carbon-14 is a naturally radioactive substance found in everything. Carbon-14 is how they do what they call carbon dating. So if you've heard of that, that is like how they estimate how old fossils are. So they can actually pull carbon-14 out of like dinosaur bones and out of like all of these really very, very old materials that when that animal died, the carbon-14 was in that animal at the time, so they can actually measure how much carbon-14 remains to figure out about how old they are because of this radioactive breakdown that carbon-14 has. So the ones we're going to talk about, there are more than what we are going to talk about, but we're really just going to talk about the three most common ways that unstable atoms become more stable. So you don't really, I took these ones out of your homeworks and such. We're going to talk about alpha decay, beta decay, and gamma decay. So the first one, So the first one's called alpha decay. Alpha decay happens when you have a really big atom with a lot of neutrons. It breaks down. When it breaks down, it actually pushes or shoots 2 protons and 2 neutrons out of the nucleus. So they call that a helium nucleus because helium, if you look at the periodic table, do you see that helium has atomic number of 2, which means it has 2 protons, has an atomic mass average of 4, which means there's 2 protons and 2 neutrons. So this helium nucleus actually comes shooting out of the nucleus of this uranium atom. So if it loses 4 mass units, what will the new mass be? It was 238, but it's going to lose 4. So the new mass will be 234. So the mass is going to go down by 4. What about the atomic number? The number underneath, what will happen to it?
It will lose 2.
It'll go down by 2 because it's going to lose 2 protons and 2 neutrons. So instead of 92, it ends up being 90. So the atomic number is going to go down by 2. Now, is it uranium? No, because atomic number of 90 is what's its symbol? It's that. It's thorium. It's Thor's. Thor's element, so it's TH. You wouldn't have to tell me what the name of it is because it's not one of the 30 that you have to know, but you should be able to find it on the periodic table. See atomic number 90. So remember that that atomic number defines what the symbol of that element is. So we went from this bigger atom to this smaller atom. It's a little bit smaller. That's going to be a little more stable. I will tell you with alpha decay, the easiest way to identify alpha decay is by recognizing this. You will always see helium, it should have a little 2+. You will always see that helium as one of the products. Okay, helium with a 4 and a 2, because that is the particle that's released with alpha decay. I'm not going to ask you to complete a reaction, but I might ask you to identify which of these is alpha decay. And you would have to be able to look at this chemical reaction completed, see the helium as one of the products, and that's alpha decay. So this is always a product. But just so that you can see how the products are formed, we'll go through and do the math with these. So CF, this is not one you need to know, but this is californium. Okay, there was a lot of research that was done in California, done around San Francisco at UC Berkeley, and that is why there is a lot that have these types of names, because the chemists that found elements said, we get naming rights, and you can't name something after yourself unless you're dead. You know, and then you're not going to name it. They'll name it for you. Like there's Einsteinium. That wasn't named after him until after he had passed away. Okay? So just so that you know. So if californium breaks down, it undergoes this alpha decay. So what happens to the atomic mass?
It goes down 4.
To what?
253.
So 257 minus 4. So it would end up being 253. The atomic number goes from 98 to 96. And if it's 96, it's not californium. So if you find 98, see 98 is CF. 96 is what? CM. Does everybody see that? So look on your periodic table, just go back 2 elements. That's curium, not one that you would have to know, just named after Marie Curie. One of the other scientists, she worked with Becquerel. She was the one that discovered radium. Okay, but that's how you would identify alpha decay. Alpha decay, the element's going to change its name. It's going to drop its atomic mass by 4, atomic number by 2. But you would always see that helium nucleus as a product. That's kind of the trick for identifying. Second one. So the second one is those pesky neutrons. So if there's too many neutrons in the nucleus of the atom, that makes it unstable. So another way for an atom to be able to become more stable is to actually take its extra neutrons and convert one of them to a proton and an electron. So what happens is there's a neutron that breaks down and it shoots the electron out of the nucleus. The proton stays behind, right? Because that's where the proton is. The proton just stays in the nucleus, but basically then electrons just come shooting out of this atom, and that helps to make them more stable because it's going to bring the proton-neutron numbers a little closer together. So in this, what happens to carbon-14 in this first example? So the atomic mass, what happens to it? So if a neutron with a mass of 1 is converted to a proton with a mass of 1, what happens to the mass? Nothing. The mass stays the same. So see that there's a little 0 above the E? So that means my mass is still 14. A neutron with a mass of 1 becomes a proton with a mass of 1. So there's no change in the mass. So you can put a little note, no change in atomic mass. But now what happens to atomic number? So atomic number, the neutron becomes a proton. So what happens to the atomic number? It goes up by 1. So the atomic number is going to go up by 1. So instead of a 6, now it's a what? Now it becomes a 7. And so is it carbon? What is it? Nitrogen. Look on the periodic table, see atomic number 7. And what do you know about nitrogen? Look at its atomic mass. Do you think this is more stable? How many protons does this nitrogen have? 7 protons, 7 electrons. How many neutrons? So see, remember when they're closer to being the same? That's more stable. So for carbon-14 to break down, it converts into a nitrogen atom, but that's going to give it equal numbers of protons and neutrons. That's a stable atom. So it won't break down any further. It's sort of done.
Is that why is that why the beta particle isn't on the reactant side, it's on the product side? Because it's not
It's on the product side because it's shot out.
okay.
Because it's still a product. So it's after the arrow. Just like in the previous one, the helium nucleus comes shooting out of the atom. So in this one, the electron comes shooting out of the atom, but the proton stays behind. Okay? Okay? But it does change the symbol. Right? So the name of the element changes, the atomic mass increases, or doesn't change, the atomic number increases by 1, and so there is a change of symbol. So let's do this one. So copper, Cu, with a isotope, it'd be copper 66. If we were going to say its name, right, because it's got an atomic mass of 66. So if it undergoes beta decay, what happens to its mass? Stays the same. What happens to its atomic number? It goes up to a 30. So now, find 30 on the periodic table. What is that? Zinc. So if you look at copper on the periodic table, its closest isotope is between 63 and 64, because it's like 63.55. So 63 to 64 is kind of the average mass. So you know 66 has got more neutrons than normal. But now when you look at zinc, what's its mass on the periodic table? 65.4. So see how this is much closer to its average atomic mass? So you know then your numbers of protons, neutrons, and electrons, well, not electrons, you don't care about them, but the protons and neutrons are getting closer to being equal. The closer they are to being equal, the more stable the atom is. So that's really why this decay happens. So you can always recognize beta decay. If I gave you that reaction and I said, what kind of decay is this? If you see an electron as a product, okay? If an electron is the product, then you know it's beta decay. That's like an easy way to remember. So if you see this as a product with alpha decay, it's a helium nucleus is the product. So if you see the helium as the product, you know it's alpha. If you see the electron as the product, you know it's beta. Okay, ready? Last one, gamma. So gamma decay is really the highest amount of energy that can be released. Compared to alpha and beta, this has the highest amount of energy, but there's not any particles. I think of gamma decay as being what happens when those protons and neutrons are like fighting for position in the nucleus. So when you have extra neutrons, that like cramps everything. And so they're like trying to like fit as close together as possible in that real dense nucleus. When they shift like this, energy is released. That energy is gamma decay. So no particles, no mass, no change in atomic number, just energy. So the energy is actually shown using that symbol. So that is a gamma symbol. It doesn't really look like a gamma symbol. It should look like this. Okay? It should look kind of like that. I kind of think of it as being, I don't know, like a sort of sideways fish. I don't know how you want to do it, okay? But that's kind of like the normal way that I always end up drawing it, is it sort of looks, it's just the gamma symbol. I don't know how else to say it, but notice there's a 0 and a 0 because that tells you no change in mass, no change in atomic number. But this is energy, energy that's released. So Pu, if you find Pu, capital P, little u, number 94 on the periodic table, very last row, plutonium, one that's used in those nuclear power plants. Okay, plutonium, you see 250 is its atomic mass compared to 94 protons. That's a lot of neutrons. Okay, a whole lot of neutrons in that. It is not stable at all. It is constantly releasing this very high energy because all of those little protons and neutrons are kind of shifting around inside the nucleus of the atom. There's no change in atomic number, no change in the atomic mass, no change in the symbol. It's just this shifting, but there is a lot of energy. In fact, this is the highest energy with the most penetrating power compared to the other two. This is the one that you really got to try and block yourself from because of its potential. Gamma rays are a lot like, gamma rays are a lot like X-rays, okay? So X-rays are kind of like one step under a gamma ray. So when people think of X-rays are not because you have like a radioactive substance, but X-rays are produced by shooting electricity. It's really a beam of electrons is what you use. You shoot electricity at a metal. Usually it's tungsten. So you actually concentrate a beam of energy at a metal, and what it does is it stimulates the metal. So when those electrons hit the metal releases energy. The energy that's released is an X-ray. So there is still this energy. You don't have any particles released, so it's not like alpha, it's not like beta. It's really more like gamma, but not quite as high in terms of its energy, but it's probably the closest to gamma decay type of radiation because X-rays, the energy from an X-ray machine, so they turn on the X-ray machine, it like powers up the electron beam generator. When they go to take your X-ray, what do? So say that you're like dental and you're going to take an X-ray of your teeth. So what do? Okay, so they stick the film like in your mouth. Now it's all digital, so it's really nice. So they're just like, okay, open up. They put this piece of sensitive film on the inside, and then they come up with the big thing and they like put it up and they're like, okay, hold your head still, right? And so where does the hygienist go? Outside. She doesn't like stand right there next to you, okay? And then you hear what? Beep. Right? Do you hear like a little beep? Okay? And then they're like, okay. And they come in, they take that, they used to have to actually develop it. Back when I was a kid, they actually had to develop it just like how Becquerel had his film. Now it's all digital. So it ends up automatically being transferred to a computer so that they can pull up the film and look at it directly. But it's the same. What does it pass through? So when you look at, like if you look at a tooth, what part, we'll just say this person only has one. What part does it pass through? Through the skin, through the gums. So that's the part that you can see it's all kind of gray. What part's white? The tooth itself, right? And if you have bone down below, that'll show up. But the tooth itself looks white unless there's a cavity, because a cavity is going to create a what? It's going to create a hole, right? Like a cavity is just literally a hole. So a cavity is just a small hole in your tooth. So if you have a cavity, it will show up like that. It'll kind of be like gray looking instead of just being solid white. And that's how they can identify. So they can look at it and go, yep, there's a cavity here because it's not solid white. If it was no cavity, it would be all white. Bone, x-rays do not pass through bone. X-rays do not pass through teeth. But x-rays can pass through muscle. X-rays can pass through the skin and all of that soft tissue. So that's why if you think you broke a bone, you get an x-ray done, because it will pass through everything except the bone. If there's a fracture, that area is going to have blood in it. That area will have separated some, and you can actually see that crack on the x-ray. So these waves pass through all kinds of soft tissue, but they're blocked by bone and hard tissue like teeth. And so that's the usefulness of it, okay? So before, if they thought you broke a bone and like the bone wasn't sticking out, all they'd be like, well, maybe you broke a bone. We'll just put you in a splint and off you go, okay? But they didn't know if your bone was just split like nice and neat, or if there was like all crushed and there was a whole bunch of little pieces in there. They didn't know if they needed to put in plates to hold things together permanently. But with x-rays, they were able to start looking at internal structures without having to do surgery. Prior to that, they had to open you up. They're like, well, let's just look.
So like this is for bones and hard tissues, like, but how do they identify like if someone got shot or something, like for the bullets?
Metal.
Okay.
Okay, so metal is just as hard, if not harder than bone.
Okay.
So it'll show up like a white spot because the x-ray can't pass through that. Okay, so it's the harder the material. So like some people, so like I had a knee replacement, so they did an x-ray on my knee replacement. You can actually see like the metal, the titanium pieces that are in the upper and lower bones. And the little, you can even see the little plastic piece that's kind of like the joint itself now. They look different. The metal comes out super white. The plastic is a little less white, so it's actually differences because of how hard it is, how solid it is. Same thing with the cavity. Okay, so you would see that spot would show up as a grayer area. If you had a crack in the bone, that would show up that way as well. Does that make sense? Okay, all right, so let's back up. You tell me, this one, what kind of decay? Alpha, okay? So without even seeing the product, you know it's alpha because of the helium. So if you see the helium as one of the products, you know it's an alpha. I wouldn't ask you to complete this reaction, but go ahead and complete the reaction. Okay, tell me what is the other product? Then do the next one and do the last one. Okay, you may want to look back at what we just talked about. Okay, so in this first one, what's the new mass? 218, right? So you would just take 222 and subtract 4, so it'd be 218. The new atomic number is 86. So what would be the new element? 86 is Rn, not one that you would have to know, but this is radon. Next one, potassium. If it undergoes this decay, this is beta, and you can recognize it because of that electron as one of the products, okay? So what happens to the mass? Stays the same, so it's still 42. What happens to the number? Goes up, so it is calcium because it's 20. Okay, and if you look at calcium, this one, 40, normal atomic mass of calcium is 40 because it's 40.08, so you would say the most common isotope's 40. This one's still a little big. I would expect this one's probably not completely stable. It's going to undergo another kind of decay to try and get closer to that number of 40. Last one. This one, when you see it, I try to put those on there too, but either way, that funny symbol tells you it's a gamma. The funny little 8 or the funny little Y, however you want to remember it. I'll use that on an exam. I won't use my drawing. So that one is the one that you want to refer to. So what is the atomic mass? Exactly the same. Number? Exactly the same. Symbol? Exactly the same. Nothing changes. This is just that rearranging that happens inside of the nucleus and energy comes out. So with Becquerel, that's the energy that was coming out of that uranium atom. Okay? So it wasn't just right in that one spot. That entire room was constantly being bathed by this energy that was coming out of that sample of uranium. And this is 1900s, so 1896 was like the first time that he like published these discoveries. Nobody knew what radiation was. Nobody really knew what radioactivity was. Okay, so X-rays, none of those things were really, I still got 3 minutes, none of those things were really like understood completely. So here's this one part though. The thing to understand and the reason to go over this is really this application, because alpha and beta particles, gamma and X-rays, all of these release radiation. Different amounts of energy, some release more energy than others. Gamma the highest, X-rays next, beta then alpha. So alpha is kind of like the lowest amount of energy that's being released, but they all released ionizing radiation. So what this can do, ionizing radiation, when it comes in contact with living tissues, can cause changes in cells, can cause changes in molecules. It can cause changes in, like permanent changes in how a cell acts. It could cause changes in DNA. It could cause changes in cell growth. So this could cause cells to die, or this could cause cells to lose their control over cell cycle. And if cells begin to grow without control, that can lead to what? Cancer. That can lead to abnormal cells begin to grow in a cluster in an area, potentially having the ability to move. So understanding this, and in fact, like Marie Curie, she died of lymphoma. She actually extracted radium. So radium is Ra, number 88. She extracted it and found when she turned off the lights, it glowed. So she used it as a nightlight. She had a little bottle of radium next to her bed because it glowed. Pretty cool, yes? It was releasing energy that entire time. She ended up developing cancer, lymphoma. Okay? So this wasn't understood. It wasn't really understood early on that this energy was actually had this ability to cause problems. But knowing this now, being in the health field, being able to help protect yourself is super important. So on Thursday, we're going to talk about blocking and shielding, things that you need to understand as a healthcare person to make sure that you protect yourself. And we'll talk a little bit about how long do these chemicals last, how much energy are we talking about, and go on from there. Okay?
Is that why they pay people?